Not only was Eurasia by chance blessed with biological abundance, but the very orientation of the continent greatly promoted the spread of crops between distant regions. When the supercontinent Pangaea fragmented, it was torn apart along rifts that just so happened to leave Eurasia as a broad landmass running in an east-west direction. The entire continent stretches more than a third of the way around the world, but mostly within a relatively narrow range of latitudes. As it is the latitude on the Earth that largely determines the climate and length of the growing season, crops domesticated in one part of Eurasia can be transplanted across the continent with only minimal need for adaptation to the new locale. Thus, wheat cultivation spread readily from the uplands of Turkey throughout Mesopotamia to Europe and all the way round to India, for example. The twin continents of the Americas, by contrast, lie in a north-south direction. Here, the spreading of crops originally domesticated in one region to another led to a much harder process of readapting the plant species to different growing conditions. When you are born, your neocortex knows almost nothing. It doesn't know any words, what buildings are like, how to use a computer, or what a door is, and how it moves on hinges. It has to learn countless things. The overall structure of the neocortex is not random. Its size, the number of regions it has, and how they are connected together is largely determined by our genes. For example, genes determine what parts of the neocortex are connected to the eyes, what other parts are connected to the ears, and how those parts connect to each other. Therefore, we can say that the neocortex is structured at birth to see, hear, and even learn language. But it is also true that the neocortex doesn't know what it will see, what it will hear, and what specific languages it might learn. We can think of the neocortex as starting life having some built-in assumptions about the world, but knowing nothing in particular. Through experience, it learns a rich and complicated model of the world. While early clocks marked only the hour or quarter hour, by 1700 most clocks had acquired minute hands, and by 1800 hands were standard. This unprecedented ability to measure time precisely found its most authoritarian expression in the factory clock, which became a prime weapon of the Industrial Revolution. As the historian of technology Lewis Mumford argued, the clock, not the steam engine, is the key machine of the modern industrial age. Soon factory workers were clocking in, filling out timesheets, and being punished for lateness. With time sliced into smaller and smaller periods, business owners could measure the speed of their workers down to the second, and gradually increase the pace of the production line. Workers who tried to reject this strict control by going slow were swiftly fired. The cruel power of the clock fed the growing culture of utilitarian efficiency, so brilliantly depicted by Charles Dickens in his 1854 novel Hard Times, where the office of Mr. Gradgrind contained a deadly statistical clock in it, which measured every second with a beat like a rap upon a coffin lid. Imagine some mutation appears which makes animals spontaneously die at the age of 50. This is unambiguously disadvantageous, but only very slightly so. More than 99% of animals carrying this mutation will never experience its ill effects because they will die before it has a chance to act. This means that it's pretty likely to remain in the population not because it's good, but because the force of natural selection at such advanced ages is not strong enough to get rid of it. Conversely, if a mutation killed the animals at 2 years, striking them down when many could reasonably expect to still be alive and producing children, evolution would get rid of it very promptly. Animals with the mutation would soon be outcompeted by those fortunate enough not to have it. Because the force of natural selection is powerful in the years up to and including reproductive age. Thus, problematic mutations can accumulate just so long as they only affect animals after they're old enough to have reproduced. What characterizes philosophy and science in early modern Europe and marks a break from earlier traditions, is the concern to tailor theories to evidence rather than authority or tradition. Galileo Galilei, Francis Bacon, René Descartes, and others formulated explanations of the heavens, of the natural world around them, and of human nature and society, not by appealing to the proclamations of earlier thinkers. Nor were religious principles and ecclesiastic dogma their guiding lights. Rather, they took their lead from reason, what some thinkers call the light of nature, and experience. Whether they proceeded according to the logic of deduction or through the analysis of empirical data, the modern scientific method they developed consists in testing theories according to reason, and in light of the available evidence. What are some characteristics of cities that must be maintained even if the population decreases? If this question can be answered, a new city model can be proposed based on the concept. Here, we focus on productivity and diversity as characteristics of cities. This is because ensuring productivity and diversity is the driving force for sustainability. For example, if there is a place to work, people gather and work there, and the population gradually accumulates to form a city. However, the industrial structure that depends on a single industry is vulnerable to social changes. Given that gold mining cities and coal mining cities have risen and fallen, their vulnerability is obvious. A city where various people gather in various industries is secure against social changes. The same is true in the natural world, and the importance of biodiversity is essential for the sustainability of the species. The same is true in cities. In a society where people of all ages and income levels live together, and diverse industries coexist while depending on each other, cities will continue to exist overcoming environmental changes, such as population decline. Both ancient farmers and foragers suffered seasonal food shortages. During these periods, children and adults alike would go to bed hungry some days, and everyone would lose fat and muscle. But over longer periods of time, farming societies were far more likely to suffer severe, existentially threatening famines than foragers. Foraging may be much less productive and generate far lower energy yields than farming, but it is also much less risky. This is firstly because foragers tended to live well within the natural limits imposed by their environments, and secondly because where farmers typically relied on one or two staple crops, foragers in even the harshest environments relied on dozens of different food sources, and so were usually able to adjust their diets to align with an ecosystem's own dynamic responses to changing conditions. Typically, in complex ecosystems, when weather one year proves unsuitable for one set of plant species, it almost inevitably suits others. But in farming societies, when harvests fail, as a result of, for example, a sustained drought, then catastrophe emerges. Power and knowledge, as well as ignorance, are interconnected in a productive and constitutive relationship. Rulers know that power cannot be executed without knowledge. Mortality tables, tax data, and the like are crucial to running an effective public administration, and conquerors have understood that information is essential for dominating a territory. Since the 20th century, Western societies have defined themselves as knowledge societies, where knowledge is essential for social organization and productivity. At the same time, the lack of knowledge proved to be important for stabilizing political and social order. For instance, secrets were essential to creating legitimacy in the early modern period, when individuals believed the world was created and ruled by divine power. By concealing the circumstances of their decisions, rulers cultivated a special aura that set them apart from ordinary people and made them seem more like unknowable gods. The complementary relationship between knowledge and ignorance is perhaps most exposed in transitional societies seeking to first disrupt and then stabilize social and political order. Or deposits represent work that nature does for us. For instance, Earth's crust contains an average of about 55 ppm of copper, whereas copper ore deposits must contain about 5,000 ppm copper before we can mine them. Thus, geologic processes need to concentrate the average copper content of the crust by about 100 times to make a copper ore deposit that we can use. We then use industrial processes to convert copper ore into pure copper metal, an increase of about 200 times. By a fortunate coincidence, elements and materials that we use in large amounts need less natural concentration than those that we use in small amounts. Thus, we are likely to have larger deposits of mineral commodities that we use in large amounts. As long as energy costs remain high, the relation between work that we can afford to do and work that we expect nature to do will control the lower limit of natural concentrations that we can exploit, and this puts very real limits on our global mineral resources. Martin Grunwald, leader of the Haptic Research Laboratory at the University of Leipzig, feels psychologists do not pay nearly enough attention to our sense of touch. With this in mind, he researched the way people spontaneously touch their faces. We all do it. You might be doing it right now while reading this. These movements are not for communication and, in most cases, we are not even aware of them. But that does not mean they serve no purpose, as Grunwald discovered. He measured the brain activity of test subjects while they tried to remember a sequence of haptic stimuli for 5 minutes. When he disturbed them with unpleasant noises, the subjects dramatically increased the rate at which they touched their faces. When the noises upset the rhythm of their brains and threatened to disrupt the subjects' concentration, self-touch helped them get their concentration back on track. To put it another way, self-touch grounded their minds.